Hello. In this lecture, we're going to consider a end slit problem. What it means is that we're going to consider interference from light from 3 slits, 4 slits, 5 slits, and etc. etc. as a generalization of Young's double slit experiment. So instead of 2 slit, now n is any integer greater than or equal to 2. This problem, as we will see, is equivalent to a diffraction grating problem. So what we have here is a slit plate. Where are the slits? Slits are here, and we have an observation screen where we record the intensity of scattered light, and on the left hand side of this slit plate there is an incoming beam which we will assume, as in the Young's double slit lecture, to be a plane wave here. And the output light from this slit plate will come to the screen at an angle theta, and that will correspond to a vertical coordinate here, y, and this length here. The distance from the slit plate to the screen is defined as L, and let's say the distance from the center of the slit mechanism to the observation point is R. Okay, so these variables are defined just as in the double slit problem. Let's describe what is exactly this slit mechanism made of. So if we actually have a look at it more carefully by blowing it up, what we will discover is that the slit plate has 1 slit, 2 slit. So let's call this slit 1, slit 2, and it will continue, and then maybe there is a slit n, and then the opaque material continues down. So instead of 2 slits, we just have more slits. So that's the only difference from the Young's double slit problem. As in the previous problem, so we will define the slit to slit distance as d. So that means the size of this slit mechanism is actually n minus 1 times d. So you may recall there is a major assumption of this kind of scattering experiment, and what is that assumption in this case? That assumption is L is much greater than the size of the scattering object. So that scattering object has dimension n minus 1d in this case. For the sake of simplicity, we will just assume that size is approximately n times d, and the difference between this and that is not that important as far as this scattering assumption is concerned. So we will assume that L is much greater than n times d. Okay, so that's the basic setup here. Let's remind ourselves of the solution that we obtained in the case of a double slit problem. So when n equals 2, we already know the solution of this problem. If you look back at that lecture, then you will discover that the intensity was derived very carefully, actually, and so that intensity was cosine square delta over 2, and let's remind ourselves what was delta, because that was the most important thing there. So delta was KD sine theta. That's the phase shift between two slits. What you may recall is that this quantity here is a slowly varying function, and this quantity here is a very important function. This function is the most important function, whereas this front factor here is a slowly varying function. What we will do in this lecture is that this function, we will assume that this is just a constant I0 for the simplicity of the lecture. So if you need to, then you can actually recover this factor at the end of the calculation. Oftentimes you don't actually need that because angles are small, or maybe if you have a circular slit instead of a flat slit, a circular screen or instead of a flat screen, then you don't, this is actually a constant. So let's ask the question, what is the solution of this n-slit problem? So we can proceed like in the double slit problem. So the total wave field on the screen is given by the superposition of waves coming from each slit. Remember that this D, in the case of light, is an electric field. And so this is ds, the wave coming from slit 1, plus and wave coming from slit n. And so wave coming from each slit is approximated as a spherical wave as before, and distance from each slit to the screen is approximately r. So for as far as the distance appearing in the amplitude is concerned, we can approximate that to r, regardless of whether we have x1 or xn. But we must keep the difference in the distances in the phase vector. And so what we have here is that kx1 minus omega t plus any initial phase phi plus sine kx2 minus omega t plus phi, and so on and so forth, going all the way to kxn minus omega t plus phi. So in the double slit case, we could do this sum of two sine functions very easily. Now we have n sine functions to sum, and if you do this using if you try to do this using trigonometric identities, you will find that it's actually pretty complicated thing to do. And the right way of summing up these sine functions is actually to use complex numbers. And how do we actually do that? Well, that's explained in my written lecture notes. So here I'm not going to explain that, and I'm going to ask you to go to my written lecture note and investigate how one can use complex numbers to sum up this series very conveniently and easily. Here we will just write down the answer. So the answer here is that sine n delta over 2 divided by sine delta over 2 times sine kr minus omega t plus phi. And what is delta? Let's write down this delta. I cannot emphasize enough what is delta. Delta is kd sine theta. So in the context of n-slit problem, you can understand this as k x2 minus x1 is also equal to k x3 minus x2 equal to going all the way to k xn minus xn minus 1. So please, see that this is actually a reasonable thing. So what we're saying here is that in the n-slit problem, the phase difference between adjacent slits is approximately the same, and which is given by kd sine theta. And it doesn't matter whether you do x2 minus x1 times k, x3 minus x2 times k, because L is much greater than the slit size, slit mechanism size here. Okay, so now what is the intensity? We can write down what is the intensity. Remember that intensity is basically proportional to square of this thing coming in front of a sinusoidal function here. And as on the previous slide, we will actually ignore the slow variation like 1 over r squared. We will just treat that as a constant. There is an additional cosine theta factor because of the fact that beam is not perpendicular to the screen, but we will also ignore that. We will just treat these factors as giving rise to constant. But this factor here, which is is the important factor, this factor gives all the interference physics, so we will keep that. We will treat other factors as giving rise to constant. So then the intensity is written like this. So now, as I write this, constant times square of that function, that sine square of n delta over 2, sine square of delta over 2. As we write this, let's note one important fact. One important fact is IR is not only just a constant, but IR, does it depend on n or not? This n, the number of slits, it doesn't. Why? Because IR is a factor that's derived from A and R and stuff like that. So it is independent of n. So IR is independent of n. It's a constant independent of n. So we got a pretty important result here. So let's write down what we got. I equals IR sine square n delta over 2 sine square delta over 2. One thing that is nice to do is that we make sure that this solution is the solution that we expect based on some known result. So for example, one can double check that this solution agrees with the solution for the double slit problem. So for example, you can do an exercise. Let's do that exercise. N equals 2, what happens here? So then what we have here is that I'm just going to write down this sine square functions here. Sine square, if n equals 2 is there, then you get sine square delta. And then in the denominator, you have sine square delta over 2. But by using the a double angle formula for sine, you can write this one as 2 sine delta over 2 cosine delta over 2 squared. And the denominator is sine squared delta over 2. And now you see that this guy and that guy cancel out when it's squared. And so what you get is 4 times cosine square delta over 2. So this n-slit problem solution, when n equals 2, can be written as I equals 4IR times cosine square delta over 2. So you might recall that we wrote the solution for the double slit problem as I equals I0 cosine square delta over 2, treating whatever is in front of cosine square delta over 2 as a constant. Then this is identified as I0, the intensity at 0 angle. So that's a way to verify that this solution that we have obtained for the n-slit problem is consistent with the double slit solution that we have obtained before. Okay, so now we will actually explore this function a little bit more. And if you're good with plotting functions, you can actually explore this function yourself in various ways by using a computer plotter. Here we will examine this function analytically. So we will rewrite it as as that, and so this can be written as IR. Let's say f delta squared. So f of delta is a function f of delta is basically what's inside here. Okay, so now if you look at f of delta, it's an interesting function. There's a sinusoidal sine function in the denominator and a sine function in the numerator. One thing that you can note is that if this sine function becomes 0, f delta will may go to 0. So let's actually make that statement. If n delta, so when is sine 0? Sine is 0 when when the argument is 0, pi, 2 pi, 3 pi, 4 pi. So when this argument is integer times pi, sine is 0, right? So that means, well, there's an integer here, and so in order for this argument to become integer times pi, so we can write as n delta 2 equals, let's say, n pi. N is integer. So 0 plus minus 1, dun dun dun. But hold on a second. So n is integer. But we need to hold on a second. Why? If this becomes 0 and then denominator also becomes 0, then we have a situation 0 divided by 0, and that requires a special attention. So we can state that this function f delta will become 0 if the numerator is 0 but denominator is not 0. And so when is the denominator 0? Just by the same logic, denominator will be 0 when delta equals 2 pi. So unless delta equals 2 m pi. So let me repeat. If the numerator is 0 and then if the denominator is not 0, then you get f delta equals 0. So that would correspond to minimum intensity. But let's now consider the case when the denominator is 0, which namely when delta equals 2m pi, when m is now in integer also. So if delta is 2m pi, notice that n delta is also an integer because n times, large n times small m here is another integer. So this small integer n becomes large n times m. So the numerator also becomes 0. So when do you how do you evaluate a function which becomes 0 over 0? Well, you can use the L'Hopital's rule. So let's take the derivative with respect to delta. So then let's do the denominator first. The denominator is half times cosine delta over 2 And then the numerator becomes n over 2 times cosine n delta over 2. And so limit delta going to 0. So, not 0, sorry. 2m pi. So, so now we consider this this expression here. If delta goes to delta is 2m times pi, then cosine here is either integer times pi. So cosine of integer times pi, what is the value of that? That's either 1 or negative 1. Here also we get the same situation. This is 1 or negative 1. So depending on the value of n, we may get 1 divided by 1, or negative 1 divided by 1, or negative 1 divided by negative 1, or 1 divided by negative 1. It doesn't matter. We don't necessarily worry about the sign here. All we need to notice is that this is depending on the value of capital N here, and the value of m, we will get n times plus minus 1. And because we're going to square it to get the intensity, we don't care whether it's we don't need to care whether it's plus 1 or negative 1. So there we go. So we got very important information here. So what we just figured out can be summarized as follows. So let me start from the case when this is actually not 0, or when the denominator and numerator both become 0. So that's when f delta squared becomes n squared. And when does that happen? When delta equals 2m pi, when m is integers. And then f delta square becomes 0 if n delta equals 2n pi, but delta is not 2n pi. Okay, so that means this is the maximum, this is clearly a maximum intensity condition. What we call, what this is that this is the principal maximum condition. And what this is the intensity 0 condition. There is no other intensity zeros, and this is the intensity minimum. The conditions that we just figured out can be summarized as follows. So instead of considering delta, it's convenient to consider delta over 2 pi. So when delta over 2 pi is an integer, so we got this principal maximum condition. So right, so that's, let's say 0 is an integer, and then 1 is an integer. Let's say 2 is an integer. But in between, let's look at this intensity minimum condition here. So that this implies that delta over 2 pi is n over n, except that when n is some multiple of n, then delta over 2 pi will become integer, and that's ruled out here, right? So then n cannot be multiple of n. Okay, so what this means is the following. So 0 is principal maximum, but when now this according to this, when delta over 2 pi increases by 1 over n, you get a minimum 0 intensity. Okay, so that's 1 over n, 1 over 2, and then dot 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 dot, and you go to n minus 1 over n. That's minimum. And then when small n becomes capital N, then that's actually not the intensity minimum condition. It becomes this maximum condition. And then after that, when this small n is large n plus 1, now you start this you start filling up the interval between 1 and 2. Once again, just as in the same pattern that you filled up between 0 and 1 here. So so then 1 plus 1 over n, 1 plus 2 over n, dot dot dot, 1 plus n minus 1 over n. So there are n minus 1 minima here, and then you hit the principal maximum at n equals 2. So that's the pattern here. So that's very important to remember. So that's principal maximum, and that's principal maximum, and then all of these other points all of these other points correspond to minimum. An absolute minimum, intensity 0 there. And then in the principal maximum case, what is the intensity here? Let's look at the intensity. I equals IR, and then F delta square is n square, so that means I equals IR times n square. So you can see that the intensity will be huge if you have a lot of slits, because it goes like n square. Having learned the basic properties of this function, sine square n delta over 2 divided by sine square delta over 2, now we can actually plot this intensity and make some sense of it. Okay, so remember what we did in the previous slide. So let's, for example, use n equals, let's say 4. Let's plot the function. So I will use the x-axis as delta, and then y-axis as I. So when delta is 0, it's principal maximum, and when delta is 2 pi, it's principal maximum. Okay, let me okay, so let's plot the function here, and on principal maximum you get 16 IR, and then here also 16 IR. What we learned in the previous slide is that you have to divide any interval from 0 to 2 pi or 2 pi to 4 pi by n, by large n. So in this case we divide it into 4 segments, 4 equal segments here, and here is maximum, but all of these other segments are zeros. So intensity wise, what happens is that this intensity becomes 0, and then there is a small maximum here, because if this is 0 0, what will the intensity do? It will go up and down, and then it will go up like this, and then it will repeat. This just repeats. And then small one here. So that's basically what you need to remember. And when n goes to n is very large, what happens is the following. So you get delta I, and this 0, 2 pi, and this one becomes n square times IR, so it's a huge number. Both of them are n. The principal maximum intensity is very large. But then this 0 to 2 pi interval is divided into n equal segments, so the segments become very small, and this function comes down to 0 pretty quickly, and then it'll go up a little bit, and then it'll decrease the maximum. And basically what happens is that when delta is appreciably different from 0 or 2 pi, principal maximum position, the intensity here becomes completely negligible in the limit of large n. So that's what happens here. Oh my gosh, my drawing skill is really challenged here. So that's what happens in the limit of large n. Let me note some generic feature in these graphs. Well, the generic feature in this graph, one of the things that you can notice is that, well, in general, there is this peak corresponding to a maximum intensity, and then there is a local maximum here, sort of in between these two maxima. And then if you look at the distance between the two minima that flanks a maximum, here the width is that, and then here the width is that, right? So that's actually 2 pi over n, but here that width is actually twice of that, 4 pi over n. So that's the generic feature of this n-slit problem solution. So principal maximum peak is not only the most intense, and it dominates the intensity as n goes to very large number. Also, the width of the peak is twice greater than all the other small peaks in the spectrum. Okay, so that's the main result. On the next slide, let's re-express our diffraction condition, our principal maximum condition, and intensity minimum condition with respect to kd sine theta and things like that. So let's summarize the principal maximum condition and intensity minimum condition as we found out. So principal maximum condition corresponds to delta over 2 pi being an integer, m equals integer. And then what we found is that the minimum intensity corresponds to the same quantity being m plus increment of 1 over n, where n can be now thought of as 1 going from 1 to n minus 1. So for any fixed m value, you have n minus 1 minima, which is created by n going from 1 to n minus 1. So that's minimum intensity. So that's how you can understand the intensity pattern that I plotted on the previous slide. Now let's express this in terms of d sine theta and so on and so forth. So delta is kd sine theta, which is 2 pi over lambda times d sine theta. So if you do delta over 2 pi, then this 2 pi will go away, and then this lambda can be put on the right hand side. So then we have principal maximum condition, which is d sine theta equals m lambda is principal maximum condition, and then d sine theta equals m plus n over n lambda is intensity minimum. And so m here, m is integer, and n goes from 1 to n minus 1. So that summarizes the key facts of an n-slit problem.